So today we're going to be going over Task D, Principles of Flight. For this, we're going to be using the resource, the PHAC, obviously, Chapter 4 and 5. Both go over a lot of great topics, both on this and even more so. I also have PHAC numbers sprinkled along, so 5.6, 5.3.3, 5.12, and so on. So starting off, we're going to be looking at the four forces of flight. That's going to be lift, that upward force, drag, the rearward, weight, the downward force, and thrust, the forward force. So as an aircraft's flying along, if we want to climb, we need more lift than we do weight. If we want to go forward and accelerate, we need more thrust than we do drag. But in unaccelerated, steady flight, we're going to be having lift equal to weight and thrust equal to drag, meaning we're not going forward faster, we're not going back slower, we're not pulling up higher, and we're not dropping down lower. Now, looking at this, let's go ahead and talk about drag first. So there are two types of drag. There is parasite drag and induced drag, both 5.6. Parasite drag is going to be form, skin, and interference. The way I like to think about form is our aircraft has big struts sticking out. Those struts are hitting the wind, constantly pushing the aircraft back and adding just a little bit more drag. Similarly, our skin in the aircraft, so the actual paints, the small rivets, and all the little buttons that all connect our aircraft together are all slowly pulling on that, or are slowly getting pulled by the wind, all pulling and causing more drag. Interference is similar to if you've ever been driving and you roll the window out, stick your arm out, you feel that pushback on your arm. In the aircraft, we have things such as a pitot tube that all stick out of that aircraft, and even if you open the window and stick your own arm out, you could cause more drag. Induced drag is a byproduct of lift, but how do we gain lift? So we have the lift equation up here, which is going to be lift is equal to the coefficient of lift times pressure times velocity squared times the surface area of the wing, all divided by 2. That's going to be the mathematical understanding of lift, but for a visual, we will use our airfoil. So there are multiple parts to an airfoil, but generally this is the shape with the trailing edge in the back, the leading edge in the front, the chord line connecting those two, the relative wind being that as we're moving forward, the wind that's actually hitting our airfoil, and then the angle of attack, which is reliant on the relative wind in our chord line. So as we pitch up on the aircraft, we're going to be pulling that airfoil upwards, and that angle of attack is going to increase. We're going to also learn about the critical angle of attack, which is a certain angle of attack that once reached, the aircraft will begin to spill. But going back to lift, so there are two main principles that are connected to the generation of lift, both Bernoulli's principle and Newton's third law. Newton's third law states that every action has an equal and opposite reaction. So as we're flying through that relative wind is going to be hitting our airfoil, pushing the airfoil up and pushing our plane up and pushing that wind downwards. That's going to be one way we generate lift. Another is going to be Bernoulli's principle, and there's an easy way I love explaining it. Let's say both Hector and Luke start at Class A and have to get to Class B. Hector wants to go straight through, so he's going to walk through and go straight from Class A to Class B. He's going to be taking the shorter end. Whereas Luke wants to stop at the lunchroom, so he's got to go all the way down, all the way forward, taking the longer end. So who has to go faster? Luke has to go faster. He's got more distance to travel. He wants to stop at that lunchroom. He wants to make it all the way around, whereas Hector can take a slow, leisurely walk. Applying this to our airfoil on the wind, that wind's going to be hitting that leading edge. Some of it's going to be going over the longer end, having to travel faster, creating lower pressure, whereas the wind under it is going to be going at a nice smooth pace, staying at a high pressure. Air always wants to be at equilibrium, so that high pressure is going to be pushing up on the airfoil, trying to get to that low pressure, generating lift as they all meet at the end. So that's going to be how we gain lift. Now, looking at thrust, if we've ever taken a nice close look at the propeller, it's essentially two airfoils connected to the prop. So thrust, if we rotate this about 90 degrees and start rotating it, is similar to how we generate lift here. We're going to be generating lift forward, generating forward thrust, and pushing the wind behind us as we increase our RPMs, use our engine, use our prop. So looking at the aircraft, let's go over the control surfaces. So we have the main ones, or the main three, which are going to be our ailerons, controlling our roll on the lateral or on the longitudinal axis. Our elevators controlling our pitch at the lateral axis, and our rudders controlling our yaw on the vertical axis. Now, the ailerons are going to be on the edge of the wings, the elevators on the horizontal stabilizer, and the rudders on the vertical stabilizer. Now, these all have different stabilities, with the ailerons on the longitudinal axis of the aircraft, the elevators on the lateral wingtip to wingtip axis, and the rudders on the vertical top to bottom axis. Now let's go ahead and look at our turning tendencies. We have 4 turning tendencies. That's going to be P factor, gyroscopic action, corkscrew, and torque reaction. P factor is reliant on the prop, and as the prop rotates, the downswing, the lower prop, is going to generate more lift than the top one, pulling the nose to the side. That is also reliant on our pitch. So as we increase pitch, that's going to be pulling more and more, getting bigger more downswing, generating more lift. Gyroscopic action relies on gyroscopic precession, which as a gyroscope rotates, any force felt along its axis of rotation is felt 90 degrees ahead. Gyroscope looks very similar to our propeller as it spins, so as we have that propeller spinning, we're going to be feeling force of rotation 90 degrees ahead, which means as we pitch and as we pull, that's going to be pushing on our prop, turning us in a direction. Corkscrew, similarly, is air spirals. So as we're flying through, the air from the prop is going to be going around our aircraft, hitting the vertical stabilizer, turning our aircraft. And torque reaction relies on Newton's third law. So again, as in Newton's third law, every action has an equal and opposite reaction. So as the prop spins, it has an equal and opposite reaction, rotating us in the other direction as the prop spins. Now, going over to our last force is going to be weight. So why do we care about weight? Why does it matter? If you've ever been on an elevator, you may have noticed that elevators have a maximum weight. Similarly, our aircraft has a maximum weight. And our aircraft also has to deal with balance. So in an aircraft, let's say there's 2 people and a little bit of fuel, that aircraft's going to be within weight and balance and it's going to be fine as it flies through the air. But let's say we add 3 more people, let's say we add a bunch of fuel, a bunch of luggage, now we're going to have excess weight. And another thing we have to consider is the balance. If we have all the weights in the back, the aircraft's not going to want to fly right, and if we have it all the way to the front, the aircraft's not going to want to fly. So now let's say we are within balance, but we have a lot of weight. Now we have to consider load factor. If you've ever been on a roller coaster, you feel as you go up and down, you feel more gravity, or you might get lifted off your seat and feel less gravity, all G-force. So with load factor in an aircraft that's completely full, bunch of people, bunch of luggage, let's say we make a really sharp turn in one direction or another, we're going to feel all that load and all that G-force coming through, and that's going to be felt on the aircraft too. Our aircraft can only handle so much before it starts braking, so if we're full weight, we're full load, and we do a sharp turn, we're going to be cracking on that airframe, braking it slowly because of that load factor, because of those excess G-forces. Now, let's go over wingtip vortices. So, again, all this wind coming over our wing and all that generational lift, the thrust rotating that wing, all of it's going to cause wingtip vortices. So, those wingtip vortices are going to be spiraling off the edges of our wing. And again, as that high pressure meets that low pressure, they're going to be spiraling and meeting at the very tip and going behind us as we continue forward. Similarly, think of a large yacht or a boat. As it goes through the water, it's going to be pushing on that water, putting water wakes. So, the larger the boat, the larger the water wakes, and similarly, the larger the aircraft, the larger the wingtip vortices that are going to be generated. If you've ever seen big Boeings or big old jumbo jets, you might notice that they have wingtip vortices, and there's multiple videos online showing that. But now think of our little Cessna. All that the big Boeing's going to have a lot of wingtip vortices, a lot of energy, and they're going to have very rough and strong wingtip vortices, whereas a small Cessna might not generate as much. So if a big Boeing comes to land at a runway, leaves all those wingtip vortices, our little Cessna is going to come through and feel all those wingtip vortices getting shaken and thrown around, possibly hitting the ground because of that excess force. So it's going to be wingtip vortices, the four forces, the control surfaces and turning tendencies, and that should be everything.